Hello, welcome back. In this video we're going to be continuing the discussion of Vsepr theory, which stands for valence shell electron pair repulsion theory. What I'm going to do in this video is explain the various shapes that the repulsion between pairs of electrons can produce. Then in the next part of the video what I'm going to do is show you how you can figure that out. So just as a quick recap of some of the Vsepr theory, remember that between various types of pairs of electrons, and really we only have two, but you have lone pairs which aren't bonded to anything, and then bonded pairs which are bonded to anything, hence the name. And so the amount of repulsion that you can get between those different pairs varies. The strongest is the lone pair and lone pair repulsion. Next would be lone pair and bonded pair and bonded pair would be the weakest. So I'm going to show you examples of these, then I'll show you how you figure that out. Linear, as it might suggest, would be a straight line. So I'm going to start off by drawing, this is H2, so this is hydrogen gas. We can represent it using a line diagram like this. Hydrogen is in group 1, so it only has one electron in its valence shell, as does the other one. So as they share, they both have two electrons in the valence shell. So this line represents one covalent bond. So 0 lone pairs. So the bond angle here would actually just be 180, which makes sense because it's just a straight line. Another example of a linear molecule would actually be CO2. So carbon dioxide, or CO2, carbon has 4 electrons in its valence shell, so it's going to make 4 bonds, and each oxygen makes 2. So we're going to have carbon as the central atom, and then each oxygen coming off it this way. The reason why it makes this shape is because there's 2 bonded pairs of electrons here and then 2 here. And they're trying to repel each other so they don't interfere with each other, and then they've got to stay far enough apart so the molecule remains stable, but then the electrons are far enough away from each other so they don't interfere with each other and repel each other too much. So the best or the biggest amount of angle these pairs of electrons can get is just to go completely opposite ends and become a linear molecule, or 180 degrees. And really, if you think about a different way to draw carbon dioxide, there isn't any other way. Knowing as you do that electron pairs are going to repel each other, there are no other pairs of electrons here. So this representation wouldn't make sense, because what's causing these bonded pairs to be pushed down? And the answer is nothing, because carbon has, at this moment, 8 electrons around it, so there's nothing else repelling these, so it makes much more sense for it to actually do this. So trigonal planar is rare, but I'll show you an example of it. Trigonal implies 3. Planar means that it's in the same plane. So this would be boron trifluoride, 1 boron, 3 fluoride atoms around it. So this would actually arrange this way. This one's a peculiar example because there's only 6 electrons around boron. But that's the arrangement that it makes. It only had 3 to start with, so it can only make 3 covalent bonds. So this is a rare example, but it does exist. And in this case, the bond angle would be 120. So the bent shape implies that it's bent, right? And so a good example is H2O. So H2O has 2 lone pairs, 2 bonded pairs. In the previous video I mentioned that the repulsion between these is stronger, so it's pushing these away. And so this would actually be a smaller angle than a true tetrahedral. So the bond angle between the hydrogens would be 104.5. I also mentioned yesterday that why does this shape take place rather than any other, and the answer is you know that this is a polar molecule based on the electronegativity values. This amount of repulsion with the lone pair and the lone pair, and then the bonded pair and the bonded pair, actually means that this is the most stable arrangement. And because of the properties that water has, then it explains why it sticks to other molecules and why those water molecules stick to other things. So the properties of water and also electronegativity values help explain why this forms and not any other. So water would make this shape. Tetrahedral, we also discussed in the previous video. I'm going to do that down here. Methane is a good example. Carbon in the middle, 4 hydrogens around it. The bond angle is 109.5. 9.5 degrees. Remember that the way that we show a molecule like this that's actually in 3D or in more than one plane, this hydrogen would be coming out towards you. This hydrogen will be going back into the board. And if you remember the shapes of these molecules that you've been working with, tetrahedral structure isn't all flat and in one plane, right? But so we represent it like this. Trigonal pyramidal is a bit more common than this one, but the best example of that is ammonia. And ammonia is NH3. So this has one lone pair of electrons, and it has 3 bonded pairs of electrons. This is kind of similar to a tetrahedral shape. It's just missing one bond off the top. But because the bonded pair and lone pair repulsion is actually a little bit stronger than bonded pair and bonded pair, but less than lone pair and lone pair, for example, water, this would have a bigger bond angle than this, but smaller than tetrahedral. And this would actually be 107 actually just 107. So between these hydrogens, imagine it like a tripod. These bond angles are 107 degrees. So ammonia, just a quick recap. Nitrogen is in group 5, so it has 5 electrons in its valence shell. It needs to make 3 bonds, or gain 3 more electrons to complete its valence shell. So it makes 3 bonds. But it just so happens that one of those bonded pairs, or one of those pairs of electrons isn't bonded to anything, or it's a lone pair. So it would make this shape. Okay, so what I'm going to do now is pause the video, erase this, and then I will explain how you figure out the shape, which is the big part of Vsepr theory. The big things to remember, though, are the amount of repulsion between electron pairs, and also the arrangement of the electrons around the central atom, and I'll explain that in the next video.